Okay, great. Okay, so welcome back. So now, after having looked at on policy and off policy control with function approximation, we want to now take a look at how to use function approximators to directly represent a parameterized policy. Yeah. So rather than parameterizing our value function or Q function as we've done so far, we will directly represent our policy with a function approximator. And so we will take a look at policy gradient methods that try to calculate an approximate gradient of our objective function with respect to policy parameters, and then look at reinforce, which is a concrete algorithm that uses this idea. And then, so it was one of the early algorithms for this, and it's still useful, but has high variance. And then in order to decrease the variance and speed up the learning, we'll take a look at actor-critic methods. So we'll take a look at baselines, which is one topic, and then also look at actor-critic methods, since they also are able to leverage the ideas of bootstrapping with the value function that we've seen before. So in actor-critic, we then basically will have both. We will have a value function estimation and as well as a parameterized policy. And then finally, we'll take a quick look at a rather recent algorithm called proximal policy optimization, which is still one of the go-to algorithms still these days to try, if you want to try a policy gradient method. Same acknowledgements. So most of the material based on the reinforcement learning book. Okay, so up to this point now, we talked about how to parameterize our value functions, but now we use function approximators for an explicit policy. And we will introduce policy gradients, which will allow us by sampling basically to calculate gradients so that we can figure out how to change the parameters of our policy directly, rather than going necessarily through a value function. And I mean, in the end, this is what we care about, right? We want an optimal policy, so we don't necessarily need a value function. That's just something that helped us with the algorithms so far, with these dynamic programming ideas and so forth. But we can as well, if we just want to have an optimal policy, we could also try to directly optimize those parameters. And that's what these methods try to do. Right, and in policy gradient methods, you often have stochastic policies, and also they can naturally, so since they use function approximation for the policy, they can also deal with the case of continuous action spaces. Yeah, so such as in robotics or many other control problems that you've already seen. Right, so the general idea is that, again, we want to use some form of gradient ascent in this case. We have some kind of performance measure that we call J that depends on the parameters that we choose, the parameters of our function approximator for the policy. Yeah, so for this we will use parameters theta. And in the end, we would like to update our policy parameters to do gradient ascent on the approximate policy of our objective function. So we want to go uphill, yeah, gradient ascent, in order to get to better values of the performance measure J as we change our parameters theta for the policy. Yeah, so this nabla J of theta t hat, that's a stochastic estimate usually of the expectation. Yeah, well, if you were to take the real expectation, you would get the gradient of the performance measure with respect to theta, but usually that can't be computed. So let's take a look at different kinds of objective functions. So there are different settings. In the episodic case, when we have defined endpoint like terminal states, then we can just take a look at the distribution of our starting states S0, and we average the values that we get by executing our parameterized policy from that starting state. So we take that expectation. On the other hand, for continuum problems, we would have to compute the, in order to figure out this objective, we should take a look at the stationary distribution of our policy, yeah, that's parameterized by theta, for all the states S. Yeah? And so we should average our values over all the states S with this stationary distribution. So stationary distribution means basically you run your Markov decision process for an infinitely long time, basically, for this given policy, and you would see what are the what's the distribution of the visitations for the given states under this particular policy. Yeah, so it's a stable distribution that's not affected by any individual transition anymore. But that's of course not available to us. Yeah, usually that's we can't compute that. We can't run everything for an infinitely long time. So how can we make progress? Still, what comes to the rescue, and that's something that we'll just introduce here without deriving it, is the policy gradient theorem. That states that basically, as long as you have a differentiable policy, pi of a given s and parameterized by theta, and any of these objective functions that we have up here, then the gradient of this objective function with respect to the policy parameters is defined as the expectation as induced by our policy, the pi, right, of the gradient of the log policy times our Q value. Yeah, again, dependent on the policy here. So that's actually a nice result, because I mean, in principle, the problem is that we can't really compute this expectation, right? Because we have a differentiable policy, so we can actually figure out, how does the distribution of actions change when we change our policy parameters, the action selection part. But in order to really compute this expectation, what we would also need is to know the transition model, right? So we would need, once we have the action as described by our policy, we would need to know how does it actually affect the state, the change in the states, right? The change in the state distribution. And usually we assume we don't have that, so we want to stay in the model-free case. So then we need to do something else, and the something else is that we actually we rely on sampling again, basically. Yeah. So in the end, we want to compute an expectation of our, well, let me come back to this. So here you see already in this gradient, there's a gradient of our policy and the gradient of Q. And in our objectives, we had V basically here, but these are related, if you remember, by just taking the expectation with respect to the policy of these Q values here. So it should be clear that both a gradient of the policy is important, as well as a gradient of Q, because the Q values will also depend on our policy, yeah, because the actions come from the policy. And in order to figure out the expectation of this gradient of the policy with respect to policy parameters theta, we basically do a little trick, yeah. So we can just multiply and divide by these probabilities as given by the policy, and then if we take a look at this ratio here, the gradient of the policy divided by the policy itself, that's basically the gradient of the log of this policy, right? Remember, the gradient of the log is just 1 divided by the argument of the log times the derivative of the inner the argument of the log, basically, right? And so you can just replace this by saying, okay, this is the gradient of the log policy times this times the policy itself, right? And if you take that can be just a sample. So here you can take the expectation because we can just sample from theta. Sorry, just a second. And this is sometimes called the score function. Yeah. So this derivative of this log policy with respect to the policy parameters, that's sometimes called the score function in the literature. Yeah, just to basically make this a bit more concrete for different ways to define your policy. You know, if we consider a Gaussian policy where we would have the mean as a linear combination of state features, so you see this up here, right? So the mean of the Gaussian would be this linear combination of state features S with our policy weights theta. Then the policy, the action probabilities would be sampled according to a normal distribution with the mean given by this linear combination of features and policy weights and with a fixed variance. Yeah. So the expression for the probabilities for the actions under this Gaussian policy would be defined as this. And now just, you know, to derive this score function, basically you take the log first, right? Then you separate out these terms basically. So the log will cancel with the expectation, and you're left with these two negative terms. And if you take the gradient with respect to theta, the first term does not depend on theta, so it becomes 0. And then you're left with the gradient of this, and this simplifies to this expression here. Yeah. Just to give a concrete example of how this is, for instance, calculated. Good. Okay. So let me come to the first algorithm that uses these ideas, basically, and that's called reinforce. So this tries to basically implement this in an algorithm by using Monte Carlo rollout. So we will sample in the Monte Carlo style that we saw before, collecting samples of this for this gradient, for this expectation of the gradient, and then we use that in order to make an update to our policy parameters. So as you remember, the Monte Carlo return is an unbiased sample of our Q function, right? It only uses the real reward, so it's unbiased. But at the same time, keep in mind that these Monte Carlo returns, if you have a stochastic system, they tend to have high variance. Yeah. So when we contrasted TD and MC learning, we said that the MC case is unbiased, but it has high variance, and TD is the other way around. It's biased, but it has lower variance. So reinforce also in practice tends to suffer from large variance in the case of the returns that you sample. And therefore the gradients will be noisy, yeah, as well, and the updates. Okay, but it's a rather simple algorithm that you can implement. You see the pseudocode here, it's rather short. So you have a parameterized policy, pi of A given S and parameters theta. Here again, I have a step size parameter, and you just initialize your policy parameters, for instance, to 0, yeah, to some arbitrary values. You loop through each episode. You loop forever for each episode, and then you generate the episodes by sampling from your policy, right? So you execute your policy in a state S0. You take A0 coming from your policy. You receive reward, and so forth. So you collect all this data for the trajectories. And then you just loop through the steps of your episode, and you accumulate your discounted rewards, yeah, over this trajectory. And then you can just use that, together with this gradient of the log policy together with this return. So you do a gradient ascent step, yeah, with the step size alpha and discount factor gamma to the t here of this gradient of the log policy times the return. So you go up the gradient in order to increase the return. That's the idea, yeah? And again, so this is a stochastic update on samples of the real gradient that involve this expectation with respect to the policy pi, yeah? So just by sampling from this policy, that of course includes the environment dynamics, right? Even though we don't have a model and we couldn't compute it in closed form, we can just sample from the policy. That will include, of course, the effects of the environment, yeah? So we use that together and use that in order to update our policy parameters theta. Okay, maybe I stop for a second for questions. Yeah. Okay, thank you. All right, so yeah, as I said, one problem is with this reinforce algorithm is that it suffers from high variance. Yeah, so as we sample long trajectories with stochastic transitions, the returns that we might get, even if we execute the same policy in the environment, will be quite different. We'll have high variance. So that leads us to also have large variance in the gradients and therefore having high fluctuations and slow convergence. So ideally, we would like to bring down this variance. And one idea is to introduce baselines, so-called baselines, that we can just subtract, basically, and then basically bring down the overall variance. But the problem is we don't want to introduce a bias. Yeah. So if we introduce a bias, then we've traded bringing down the variance with an additional bias. And as we'll see, in some other methods this is done, but here the goal is to have reduced variance but still remaining unbiased. So we can still include some kind of action-independent baseline. Just change the policy gradient in a way where we have Q still, yeah, but introduce now this, subtract this baseline that is maybe dependent on the state. So overall, if we bring in the gradient here, we get this, so this is the old part from the old policy gradient theorem, basically. And this part just multiplies the baseline with the gradient of the policy. But since the baseline is not action dependent, yeah, this is a probability distribution. And if we just sum over all the A's, the gradient here is then is going to be 0. Yeah. So this whole thing doesn't actually introduce any kind of bias. Yeah. And so we can just leave this out, and we're left with what we had before in the policy gradient theorem. So no bias is introduced. However, by introducing this baseline that we subtract from the samples of the Q values, which we said have high variance, we bring down the overall values and we reduce the variance. The thing is, you could even do this with a constant value, but the problem then is that this is not, for some states this might be good, for other states this might be very bad. The constant value is not the best thing to do. But as we'll see, if we use, for instance, an estimation of the value function, that's actually usually working much better. Okay, that's what I just said. Yeah, constant value could even be used, but usually state value function is what works really well in practice. Right, so we could discuss whether the Q function would be a valid baseline, but it's not because it includes an action. Okay, and yeah, if we assume an approximation of the state value baseline. Okay, maybe we can come back to these later. Here you see a reinforce with baselines algorithm that includes this idea of adding the baseline. Yeah, so basically you have now, in addition to the parameterized policy, pi, that has parameters theta, you also have an estimation of your state value function, v hat, yeah, of s with parameters w, just as we had in the value-based methods. And then you use that as a baseline, basically. Yeah? So you estimate it from data, and then you subtract it when you, in order to generate your delta here. So first of all, you calculate the return just as before from all those steps in your episode. And then you calculate this delta, where you subtract this baseline in form of the state value function. And then you make the update with that, yeah, rather than with just the return itself. Okay, so you need to update. This is the part for the parameters for the policy. Yeah, so theta are the parameters for the policy. Here you use the sample of the policy gradient, and you also need to update the parameters of your state value function estimate. Yeah. Okay. Yeah, so here you have the difference between the return and the baseline, and that's entering the update for the policy gradient here. Yeah, and that's reducing overall, that will help you reduce the variance. Okay. Then we'll come to actor-critic methods. And as I said, actor-critic methods are different in the sense that, I mean, they're similar to what we just saw because they also maintain an approximation of the value function, but they don't just use it as a baseline to get the variance down, but they again are used for bootstrapping, as we know it from the value-based methods that we looked at before. And the nice thing is now you have bootstrapping with the parameterized value function, and you have a parameterized policy. And because of that, you can deal with continuous state spaces and continuous action spaces. Yeah. So that's and the variance is low. Yeah, compared to these actor-critic methods with these policy gradient methods with baselines. Okay. Right. So reinforced with baseline is unbiased, but tends to learn slowly and has high variance still. We can reduce the effects of the variance by not doing these Monte Carlo rollouts, but rather having just these one steps in the TD form, and then bootstrapping with a value function estimate. Yeah. So that's the idea for this one-step actor-critic method. Yeah, so we don't use the full return anymore. Yeah, rather than having G running from T to the end of the episode, we basically now use a G that runs only from T to T plus 1. Yeah, so just one step return. That's just the immediate reward, of course. Yeah, and then we rather use the value function to approximate what's coming afterwards from the next step, and again we subtract our old estimate. Yeah, so that should look very familiar from the value-based methods that we looked at before, from TD0, basically. Yeah, and still we need to multiply it with the gradient of our policy, or the log, the gradient of the log policy. That's what this is basically. Yeah. Okay. that's the idea of these one-step actor-critic methods, and here you have the full pseudocode. So this is for the episodic case, and you try to approximate your optimal policy that has parameters theta in this case for the approximation. Yeah, again, you have parameterized policy pi with parameters theta and differentiable state value function estimation. That's your v hat of s with parameters w. You initialize basically policy parameters and the state value weights as you like, with 0 is something common. And then you just loop again. And here now you calculate the temporal difference error, like you saw before. Yeah, so this is the delta here in this case. And so this is used for the case of updating the weights of your function approximator for the state value function, but it's also used here in the update of the policy weights. Yeah, so you use the bootstrapping by your so-called critic. Yeah, that's what this value function estimation is called. The actor is the policy, and the critic is the estimation of the value function. And you use the estimate of the critic, yeah, that tells you how good is it to be in that state, and use that action as described by your policy. You use that in your update of the parameters for the policy. Okay. Yeah, I think we'll take again a short break for questions. Right. Then we wanted to introduce a quite recent algorithm. I forgot the exact year this was introduced, but it's not long ago. It's called proximal policy optimization. And it's a sort of simplification and an update of an earlier algorithm that was called TRPO for trust region policy optimization. Yeah, achieves similar performance, sometimes even better performance, while being a little bit simpler. So yeah, and so this was introduced by John Schulman and some of his colleagues at UC Berkeley. And the idea is as follows. So we do collect our data with, a parameterized policy, pi with parameters theta old. That's what we would call them right now. So these are the parameters before we do an optimization step, basically. However, we want to optimize our objective and improve our policy, of course, right? So we want to update our parameters so that we get to a better policy, hopefully. And we can then write our objective that's depending on pi theta in terms of the old parameters, yeah, pi of theta old, as follows. So that's something that they derive in the paper. This is not obvious from this slide, but I hope it becomes more clear on the next slide. It turns out that you can decompose the objective that's depending on the new policy, the policy with the new parameters, based on the objective value for the old parameters of your policy, plus an expectation with respect to the new policy parameter, the policy with the new parameters of the sum of the discounted advantage values. Yeah? And the advantage value is just what we see down here. It's just the Q value divided, so for a given state in action, minus the state value, yeah, for that same state. So that's something that you often see, and it tells you basically how much better is your current action that you're evaluating, this A, compared to the average, yeah, which would correspond to the V value. Yeah, remember the V and the Q are related for a given policy are related by taking the expectation with respect to all the action probabilities of your policy. So, on average, how much better would be your A that you're evaluating with respect to the average that you would take in that state? That's why it's called the advantage. Yeah, and so you can think of this again as using this V as a baseline here, yeah, in a policy gradient algorithm. So you're using the advantage directly here. Okay. Okay. Right. So that's the general decomposition that they present in the paper. And now just quickly going through how this is, why this makes sense. So this is, that's the term that we have on the right side here. This is the expectation of the sum of the discounted advantages with, with the expectation with respect to the new policy, the policy with parameters theta. And we want to show that it's basically equal to these two terms, yeah, that's what we need to show. And so we can first write this out a little bit more explicitly. Yeah, so the expectation with respect to the actions sampled by your policy, the new policy pi theta, and the next states as they come from your from the distribution, from the probability transition distribution of your environment. And then you can write this advantage as just the, yeah, basically again, so this would be Q, right? The immediate reward plus the discounted state value for the next state minus your the state value for the current state. Yeah, so that's the definition of the advantage up here. And then, so you have this infinite sum here, yeah, starting from 0 to infinity. And if you basically, well, what you can do is you can take this part just goes here, basically, right? And these terms, if you telescope this out over the sum, what you can realize is that apart from this very first term, where you just have this minus v theta old for S0, yeah, starting in 0. For all the other terms, you will have, you will have a positive and then a negative term as well. So they cancel out, yeah, over this whole sum. So what you're left with in the end, if you telescope this out, then this will be just this particular term for S0, for the very first state that you consider, yeah. So that's why we don't have a sum, this infinite sum here anymore, and why this also vanishes. Yeah, so now this has only S0 and pi theta old here. Right, and then we can take a look also at this expectation here. And now, since this is only dependent on S0, and not on everything else, that's would be that we would have to consider for this expectation. We can just basically simplify this. We can separate these terms and just consider the stochastic part that we're dealing with here, which is just the sampling of the very first states, S0, and that just comes from the state distribution of that particular state. Yeah, so we don't need to deal with any transitions anymore here, but here we do, right? And these are basically just the definitions, so the expectations of these state values for S0 and also for the expectation of the long-term reward or the return, yeah, the discounted return. These are the definitions of our objective functions as we defined them. We didn't define them here, but we defined them earlier. So the expectation of the V is basically our objective, yeah? So this is the definition of this minus eta of this pi theta old, and this is the definition of the pi theta, yeah? So the eta of pi theta, so the objective with respect to pi theta. And since this is, if you would bring this one to the other side, or rather this one to the other side, yeah, then this is exactly, is exactly what we had up here, yeah. So that just shows how to get to this decomposition. Okay, and now how do we use that, right? That's the question. And the way that they use it in PPO is that they basically just ignore this this change in state distribution. Okay, so they just say, well, we just assume that our state didn't change, and we can just use our pi theta old. Yeah, and so it's not really the right objective; it's a surrogate objective, but it simplifies things, right? And of course, they try to make up. They take, they have to deal with the fact that they commit an error by just simply ignoring that change in the state distribution as they change the policy parameters. But they try to correct for it with this term here, which is similar to what we saw with the importance sampling weight. Yeah. So we actually would like to take the expectation with respect to our new policy with the new parameters, but we are taking the expectation with the policy that we gathered the data from, which was pi old. Yeah. So we introduce an importance weight here, basically, in order to correct the probabilities for the returns or the advantages that we got when we executed our old policy. Okay, that's the main idea. And what they show in the paper is that, basically, if the difference between the old policy and the new policy is small, then they are very close to optimizing the actual objective, this eta of pi theta, because there's basically this penalty term. So, the improvement in this objective function with respect to the new policy parameters will be this old value of the old policy parameters minus a term that depends on the maximum difference between the distributions, if you like, the one of pi theta old and the one of pi theta. And the smaller this is, then the bigger will be this eta. So the bigger will be the improvement, because then we're closer to optimizing this real objective. To put this in a practical algorithm, they introduce some more heuristics, if you like. So they introduce something that's called the clipped surrogate objective, where you try to take the expectation with respect to the data gathered with the old policy, and then you take either the minimum of either this importance ratio corrected advantage, or you say I'm clipping this weight, this importance weight, I'm clipping it between 1 minus epsilon and 1 plus epsilon. Yeah, so you just want to prevent your importance weights from being too large, basically. Yeah, and then you correct for that with this clipped objective. Or you can use this so-called adaptive penalty surrogate objective, where you actually compute this KL divergence between the distribution with your old policy parameters and the distribution with your new policy parameters. And then you just you again run your policy for t time steps and n trajectories. You will estimate the advantage function. Yeah, so you have your v and you have your q, and so you do the stochastic gradient descent then on either of the objectives. And if you use this adaptive penalty surrogate, then you need to also calculate, you need to adapt this parameter beta that you have here if this KL divergence is too high, and otherwise decrease it. That's the whole algorithm for PPO. And it's really still a very, very good algorithm for doing policy gradient. If you have continuous action problems, it's still a very good method to try. Of course, there are methods now also that are more performant, most of them being based on this actor-critic ideas, but still, it's a good algorithm to try still on many problems. And it has, these policy gradient algorithms, they tend to be much more stable than algorithms that have these value functions. Yeah, that's just something that's that you can observe in practice. So if that's an important criterion for you, then yeah, these policy gradient algorithms are also worth trying. Definitely. Okay, that's all I wanted to introduce for policy gradients. Let me again pause and